Block 1. The Cosmic Canvas, Our Universe's Origins. Welcome back, Cosmic Explorers, to the channel where we tackle the biggest questions in the universe. Today, we are venturing to the absolute edge of known physics, to a place where time itself might be a loop, and our entire existence could be just one chapter in an epic cosmic saga. We've all heard the story of the Big Bang. It's the cornerstone of modern cosmology. About 13.8 billion years ago, everything we know, every star, every galaxy, every planet, was compressed into an infinitesimally small, hot, dense point. Then, in a moment of unimaginable energy, it exploded outwards, creating space and time as it went. This is the grand narrative of our cosmic origins, a story scientists have painstakingly pieced together by observing the universe around us. The single most important piece of evidence for this story is a faint, persistent glow that fills the entire sky, no matter where we look. It's called the Cosmic Microwave Background, or CMB for short. Think of the CMB as the universe's first baby picture. It's the oldest light we can possibly see, an afterglow from the Big Bang itself. This radiation was released when the universe was just a toddler, a mere 380,000 years old. Before this moment, the universe was a superheated, opaque soup of charged particles, protons and electrons, and light in the form of photons was trapped within it, constantly scattering like light in a thick fog. But as the universe expanded, it cooled. Once it reached a cool enough temperature, around 3000 Kelvin, protons and electrons could finally combine to form neutral hydrogen atoms. Suddenly, the fog cleared. The photons were set free, and they have been traveling across the cosmos ever since, carrying with them a snapshot of what the infant universe looked like. This is the CMB. When astronomers first detected it in the 1960s, it sounded like simple static, a uniform hum coming from every direction. But with more sensitive instruments like the COBE, WMAP, and Planck space telescopes, we discovered that this ancient light isn't perfectly uniform. It's dappled with tiny, almost imperceptible temperature fluctuations, areas that are fractions of a degree hotter or colder than the average. These minuscule variations are, without exaggeration, the reason we exist. They were the seeds of all cosmic structure. The slightly denser, slightly cooler spots had a bit more gravity, and over billions of years, they pulled in more and more matter, eventually collapsing to form the first stars, galaxies, and the vast cosmic web we see today. You can think of it like this. Imagine the early universe as a perfectly smooth, tranquil pond. The Big Bang is a stone dropped in its center. The tiny temperature fluctuations in the CMB are the faint ripples spreading out from that initial event. Over time, some of those ripples grew, coalesced, and eventually formed the islands and continents that are the galaxies we inhabit. This model is incredibly successful and has been verified by countless observations. It is the bedrock of our understanding. But what if it's not the whole story? What if the CMB, this beautiful echo of our own beginning, is holding secrets that are far older? What if it contains whispers, patterns, or even distinct ghosts of a universe that existed prior to our own? This isn't just a philosophical question anymore. It's a testable hypothesis at the frontier of theoretical physics. Get ready to have your perception of reality challenged, because we are about to explore the mind-bending possibility that our universe has a cosmic ancestor, and that its faint, ghostly signature is hiding in plain sight, imprinted on the very canvas of our creation. Block 2. Unveiling the Echo, Evidence from the CMB. So, if there was a universe before ours, a cosmic predecessor that lived and died, how could we possibly find evidence of it? The idea sounds like pure science fiction. But according to one of the greatest minds in modern physics, the clues are right there, in the data we already have. The proponent of this radical idea is Sir Roger Penrose, a Nobel laureate and mathematical physicist renowned for his work on black holes alongside Stephen Hawking. His theory, called Conformal Cyclic Cosmology, or CCC, proposes that the Big Bang was not a singular beginning, but rather one event in an infinite sequence of cosmic cycles, or eons. Each eon is a universe that expands from its own Big Bang, lives for trillions of years, and eventually dies a cold, empty death, which in turn becomes the Big Bang for the next eon. To understand how this is possible, we have to journey to the far, far future of our own universe. According to the Standard Model, the universe will continue to expand and cool. Stars will burn out. Galaxies will drift apart. Eventually, after an almost unimaginable length of time, even matter itself might decay. The only things left will be stray photons and other massless particles, drifting through a vast, cold, and empty void. And at the center of what were once galaxies, there will be supermassive black holes, the last holdouts of concentrated mass. But even they are not eternal. Thanks to a process theorized by Stephen Hawking, they too will slowly evaporate over mind-boggling timescales through a process called Hawking radiation, releasing their energy back into the universe. At the very end of our eon, the universe will be an almost featureless sea of low-energy photons. Here is where Penrose's genius comes into play. In a universe with no massive particles, the concepts of scale, of time and distance become meaningless. An infinitely large, empty universe is, mathematically speaking, almost indistinguishable from an infinitely small, dense point. Penrose uses a mathematical tool called a conformal transformation to squash that infinite future down, effectively turning the cold, empty end of one eon into the hot, dense beginning of the next. The end becomes a new beginning. So, where's the ghost? Where's the proof? Penrose argues that the death of the most massive objects from the previous eon should leave a mark on ours. Specifically, the final evaporation of a supermassive black hole is not a quiet fizzle, but a colossal release of energy. He calls these final pops Hawking points. This immense energy, he theorizes, would be powerful enough to punch through the conformal boundary separating the old eon from our new one. It would act like a powerful shock wave, propagating into our early universe and leaving a distinct circular pattern imprinted on our cosmic microwave background. These wouldn't be hotspots, but rather subtle circles of unusually low temperature variation, regions far smoother than the surrounding CMB. And remarkably, when Penrose and his collaborators analyzed the data from the WMAP and Planck satellites, they claimed to have found exactly these patterns. Multiple, faint, concentric circles of low variance, just as his theory predicted. This is the ghost, a tangible echo, a scar left on our universe by a cataclysmic event from a previous one. Of course, this is a highly controversial claim. Many cosmologists argue these patterns are simply statistical flukes, random alignments in a noisy dataset that look significant but aren't. They argue that if you look hard enough at any random data, you're bound to find patterns. But Penrose maintains the evidence is stronger than random chance would allow. If he's right, it means our universe carries the legacy of its parent, a cosmic ancestry written in the oldest light we can see. It would mean the Big Bang wasn't the beginning of everything, but just the beginning of… What do you think? Are these faint cosmic circles a genuine ghost of a dead universe, or are our minds just seeing patterns in the static? Subscribe for more cosmic mysteries, and we'll see you in the next one.